evolution. Oh, um, so the robot is saying we're being recorded, huh? Okay, so the structure of the interior at in the end of the asymptotic giant branch, which is characteristic of very high mass loss for massive stars, shows different chemical compositions depending on the nuclear processes. But to then just pass on. Um, okay, so this is the collection of the stars that are called luminous blue variables. In general, they're best known outside of the galaxy, or rather, that was true before Gaia, because we didn't really know the luminosities, because we really didn't know the distances. That's all changed in that we now have parallaxes for every one of these stars, but they were first identified in the LMC and Andromeda and M33. The original name was depending on which type of what I'm sorry. The names were numerous. The phenomenology was individual, and there was no real unification or understanding of what was going on. The ones that were discovered in M31 were called the Hubble-Sandage variables, and not because they looked like Hubble or Sandage, but they are extremely bright. You know that because they're in another galaxy, and showed variations of order magnitudes over time scales of decades. They showed they show no short-term variability, where short-term is like Cepheids. They can be as bright as supernovae, and in fact, you see the luminosities on the left-hand axis here going up to a couple of million solar luminosities. That's real, okay? Um, these the brightest of these stars can get up to 10 to the 7 solar luminosities for a period of time. And so these were about as bright as supernovae, but they were recurrent. Now, I mentioned that because that was rediscovered something like a decade ago with a class of objects now called supernova imposters, which are objects, which are stars that are identified in surveys for transients as supernovae. If you don't have spectroscopy, who's to know, except they recur. And we know damn well that supernova events are singular. But they're as bright as supernovae, or nearly so, at least as bright as the underluminous ones. So the LBVs may in fact also be hiding among the supernovae. That's just why the Hubble-Sandage variables were first identified. And there are three principles for those. Um, they're known by the wonderful names of variables A, B, and C, uh, but they all lie on kind of this side of the diagram temporarily. Uh, some of these names you may know, but we'll get back to that. The second group were called Asterotis stars because Asterotis is a star in the LMC, and it was very well known as a variable star going back to the first observations by the Harvard group tracing what became Henrietta Leavitt's discovery for Cepheids of the period luminosity relation. the importance of the S Doradus stars is that they're variable on timescales. It's going to sound now familiar on timescales of decades with amplitudes of a couple of magnitudes. And they're obviously the most luminous stars in the LMC. So stars that were analogous to them began showing up in longer term surveys. You see, the fact that these things vary on decade timescales means that you're not going to find them in short observing runs. The only way you'll know about them is from archival observations. And it takes a long time to build those up. So, although S Doradus was known to be a, a variable and that there were some other objects in the LMC that were similar, it wasn't clear that they were actually the same class of object. All of this came together in the 1980s when Peter Conti, at the time in Colorado, labeled all of the stars on this diagram the luminous blue variables. That was, although it's just a change in nomenclature, that was a turning point because suddenly it was realized that you were looking at essentially the same object in very different contexts, very different environments, but that they really are the same. And we should have known that long before. Conti actually concentrated on it because of this. Estor and an old friend of all of yours, uh, P. Cygni. P. Sig is the prototypical stellar wind line profile. Okay? Um, and let me try one more time to see if I can get this whiteboard to work. So in order not to be boring you, let me ask, are there any questions that I can deal with now while I'm trying to get this keyed up?
No, it seems correct. Go on.
Okay, I may have to resort to the most primitive means here of treating this actually as the equivalent of a blackboard. Yet another case of Murphy's Law applying. Um,
What's the problem, Steve?
the problem is that I have this electronic pad that that flakes out periodically. Um,
Mm.
it was working at the very beginning, obviously, but now it's not seeing the computer. So let's just forget it. And I'm going to do this the hard way.
Okay, take your
So
time.
um, so you can all see this now.
Yes.
Okay, so let's go through what will happen if here we have a surface which we'll call a photosphere. Okay, and we have radiation that's streaming out from that and accelerating a medium above it. When the surface gravity is balanced by this acceleration, there's still a pressure gradient that's going to push material through this surface. Okay? And
Mhm.
so what you're going to get is a velocity with distance law that accelerates outward. We've talked about this in the Nova case also, but that's explosive. And this is a gradient. Since there's mass associated with this flow, it's not just photons, the change in the density is such that this region has a higher density than this one, simply because the area of this part of the flow is larger and the velocity is higher. Okay?
Mhm.
Consequently, we have a difference in the opacity as a function of wavelength. So, although a static atmosphere would have a line stationary here, this portion seen against the deeper layers is going to be lightly shifted, but the region above it now is shifted by more. It's accelerating outward. And so you'll have a combination of these layers. In addition, so the instead of having a single column, which would be this thick, you have an ensemble of columns, each of which is this thick. And
Mhm.
consequently, instead of having a single deep line, you're taking the absorption and smearing it out over a velocity range. It doesn't matter that this is intersecting the surface of the star. That's something I have to explain carefully. The standard way that you see a description of what's called a P Cygni profile, because these were first described in P Cygni, not because they were first seen there, but the first paper describing the general class of these profiles by
Steve, can you please put your sheet just in front of the camera for a few seconds?
okay, I have an idea. How does this work?
That's okay?
So if I do this, you can all see that?
Yes, a little bit more to you. Yes, I think
Okay.
it's okay. Yeah,
So
good.
the standard description is that you have absorption in this column.
Okay.
And so, yeah, that's fine. Except what you mean by this blob is not the surface of the star. It is the optically thick portion of the flow. The star may, in fact, be sitting inside that. Okay?
Okay.
This is the LBV. This is the whole point. When we look at the spectrum in the optical or the UV of one of these stars, we find that all of the lines are shifted. You don't see a genuine surface. You're looking at the portion that is an effective photosphere, not a static surface. And for that reason, what you're seeing is a massive wind whose surface of optically thick emission, in other words, this pseudo-photosphere, can expand or contract depending on the mass loss rate. The luminosity of the central object is remaining fixed, but if for any reason the mass loss rate goes up, the surface, this surface, moves outward. Okay? This is the whole point about the LBVs. They change their rate of mass loss over time. The events that we see that qualify them for the word variable in their name is a mass loss change. It's in that sense very much like a nova. If you have a very extended optically thick surface, then one of the things that happens in the line profile is that it goes to something that looks like this, where this is the velocity. So this is positive.
Steve, we can't see your plot. It's below
Can
the camera.
you see this now?
Yes.
Okay, so here, so this is negative and this is positive radial velocity. Okay, so far?
Yes.
If, on the other hand, we reduce the mass loss rate, then this region, this optically thick region, becomes smaller relative to this background. And so you get greater emission and reduced absorption. Now, when I said that the problem with these stars, I'd mentioned this at the very beginning, is that we are sitting in the optical and we don't necessarily see what's really going on. Now I can show you if we go back to the um, the Acrobat. So, are you? Let me make sure that we're screen sharing again. Um, okay, so
That's okay.
this is what the spectrum of one of these stars looks like. These are stars in M33, variable B and variable C. Uh, the lines that you're seeing are the usual, the Balmer lines, uh, but all of the rest, all of the ones that are marked here, are all very low ionization. There are lines like forbidden and permitted iron 2 and the iron group, which have extremely low ionization potentials. So this is a really bright star. It's a hot star. It shows helium, and yet it's also showing all of these iron lines. That should sound familiar because that's exactly what novae do. That this is so optically thick a medium that in the optical, what you're seeing are the lines that are excited from the UV. The okay, so this is the poster child of luminous blue variables. It's Eta Carina. During the famous grand outburst in the 1840s that was recorded by John Herschel from the Cape. Uh, the star has never done anything quite like this since, but the brightness of the star now is like, oh, fourth magnitude. It's one of the brighter stars in the southern sky, except that at its brightest, you can see that its visual magnitude was -1. This is a star at uh, many kiloparsecs. So the easiest way I can put this is its luminosity was over 10 to the 7 solar luminosities. This was the brightest object in the galaxy for a short time. Uh, the problem is this is a visual observation. And so the question that comes to mind is, if this were a nova, we would be saying, well, this was just part of an expansion. Was this as an explosion? Was this a merger event like one of the ones that I've already talked about? We we wouldn't know anything about that from just this observation. Um, this is Eta Carina. It's because it's in the galaxy and now we know its distance. Uh, we also have enormous amount of information about what actually happened. This, when I talk about an optically thick surface, that's what you're seeing here. The actual star, which is actually a multiple system, is embedded somewhere in here and is not seen except in the X-rays. That all of all of this is optically thick material that is just reprocessing the central object. This, called the homunculus because somebody had a sense of humor, is sitting inside an extended envelope and a sort of light echo of that envelope. The central object is a different problem. There's a binary system in there with a period of about 5.5 years and a very eccentric orbit that shows periodic outbursts, but nothing like the grand event of the 19th century. This is the tracks of the rest of them, that when you've got the observations over an extended time, the characteristic of the LBVs is that they show P Cygni-like profiles, and they do have excursions that go into the red. But so this region that I said was empty is empty statistically. That when one of these goes into outburst, just like a nova, you go into a redistribution phase. The mass loss rate goes up, the envelope recombines, you get the emission lines from these low ionization species, and the star turns incredibly bright in the optical and in the near infrared. But it doesn't last. The event ends, and then it winds up back in the portion of the diagram that would be either O stars or B stars. Always supergiants. So there's no question that these are very massive objects and maybe as massive as 100 to 150 solar masses. But nonetheless, they are variable mass loss objects that behave slowly in precisely the way that a nova does. The difference being that it's not the ejection of an envelope in an explosion event. Okay? Now, having saturated you with all of this, let me explain that this is why, that the reason I'm talking about this is these are ideal amateur targets. They're not that bright, admittedly, and I'm not talking about the ones in the LMC, but P Cygni, for example, and then to show you another example, AG Carina and HR Carina. Um, this is in fact to make my point that the curve at the top is the optical and the curve at the bottom is the UV. And here in AG Carina, this is the optical and this is the UV. It's the only such light curves we have right now because they were taken with IUE and it took something like 10 years to get this much data on them. And you see how miserably sparse the UV observations were. But when you put those together, when you add the UV and the optical and the infrared, and you correct for the reddening, this is showing what happens to the difference between the optical and UV as you change the reddening. There's a point where the total luminosity across this event is constant. And that's the point where you can get the reddening. This is a technical point, but the importance is when you add the UV and the optical together, the stars go horizontally across the HR diagram. In other words, what you're seeing here is the star not changing its core luminosity. In a nova, you have an explosion. That is, the central star goes through a thermonuclear reaction that goes into a runaway that expels the envelope. The luminosity of the central star has increased by orders of magnitude because of the nuclear processing, which then turns off. It appears with these stars that what's changing is something in the envelope, in the structure, but it's not in the core. Okay? So what we're doing here is seeing stars expelling material in the way that the AGB does, that it goes through episodes of expelling material at high mass loss rates, creating a dense circumstellar environment, but from that, not changing the luminosity of the core. Um, this is what these things look like in the far ultraviolet or in the ultraviolet. So these are satellite observations from IUE in the region from Lyman alpha to 2000 angstroms. The characteristic of these stars and the reason they show the iron is this region in the middle part of the UV where the absorption is enormous. This is what we've all called the iron curtain. Uh, it's the region in the UV where the resonance lines of the metals are formed. And it's the change in the opacity of this region that governs the light curve. When the star expands, the temperature drops in the region in which the lines are formed, and the opacity here suddenly goes up, which makes the visible get brighter. And then when the mass loss rate goes back down, this region ionizes, these lines weaken, and the result is the optical goes down. But the total luminosity of the star has remained approximately constant. This is P Cygni. And the way I'm using this as a way of hopefully explaining what I meant by where the pseudophotosphere occurs. The way you normally draw a P Cygni profile looks kind of like this, right? That you've got an absorption and an emission, and they're kind of the same. Instead, looking at H alpha or looking at the Balmer lines, there's something really wrong, that the emission is enormously strong, and these are optical spectra from the 1990s that we got when studying these stars. This is the Paschen series showing that, yeah, all of the recombination lines are there. But when you look at the velocity here, it's only a couple of hundred kilometers per second. And for a star to lose a significant amount of mass, that doesn't make sense. The escape velocity from the star and the terminal velocity we would expect for a wind is much higher than that. So somehow, either our theory is completely wrong, or there's something else going on in the line formation, which is what I was trying to explain with this relative size of the emitting and absorbing region. The emitting region for hydrogen is enormous. It's the whole visible extended envelope of the star. The part that's optically thick is a very thin cone. Again, it's not to the surface of the star. It's simply the part of the wind, the inner wind that's dense. And so if you look in the optical, you see deeper because the opacity is lower. If you look in the UV, you don't see as deep, and because the wind accelerates outward, you get a higher velocity. So in the UV, you would expect to see a profile that looks more like this than in the visible. Okay? Um, okay, this is one more thing. Um, Last time when I was talking about planetary nebulae, I used this as an example that this was just a typical example of the difference in the ionization that you trace from different lines. And that's because you've got a hot central source. And in this case, as I was saying at the beginning, the medium is ionization bounded. And when you look in other wavelength regions the like the infrared, where you're not worried about the ionization bound, the ring nebula winds up looking like this. It has all sorts of garbage around it. Those would be what an LBV would look like. That these earlier events are going to be way beyond the bounded ionized region that you see instantaneously now. And this is the demonstration that these are different luminous blue variables observed with HST. S61, R127 is one that showed large amplitude variations in the 1980s to 90s and became one of the standard LBVs. It has an extended envelope indicating that these events that we're seeing now have been going on in the past for an extended time. If you're looking at the LMC and you, even with HST, can resolve an object 1 arc second at the distance of the LMC is about a parsec. That is a pretty large size for something moving at only a few hundred kilometers per second. It takes a while to get out there. And so the assumption is that all of these structures that you see around these different stars, and all of them show extended structures, are indications that the LBV events go over an extended time and that a large amount of mass is going to be stored out at large distance. AG Carina is the only one in this set of observations that actually sits in the galaxy. So this is at a distance of, I think, about 5 kiloparsecs. It's very near, but very well resolved. And this stuff around it, which you can't really tell in the LMC, is very dusty. Now, we know that because you can see the infrared from it. And we also have an idea of that from the extinction. But there's something else here. Uh, okay, these are the observations with the WIFPIC. Uh, they give you a rough idea of how this extended material is structured. But as with a planetary nebula, this outer region, although it looks like there ain't nothing there, is actually filled, except you're not seeing it in this wavelength region. Okay?
Um, sorry.
The other is that you see that there's distinct fragmentation in the inner region, but there's dust. And this is the demonstration of that dust. Um, this is a comparison of the ultraviolet, of the central star, and the ring. And if you look at it, you'll notice they don't look all that different. Okay? Uh, you've really got to strain and sacrifice a couple of chickens to really drag out the secrets of these spectra. But
Uh,
you don't need that. Look at them. They're basically the same, except the distance between this and this is about 100th of a parsec. They are not in the same aperture. So what you're looking at here is scattered light. Okay? This is not intrinsic emission, and that's the other thing about the LBVs. When we're looking in another galaxy, we cannot see that this region is really that extended. And so, because the star is varying on timescales of a year, and the size of the region around it that it may have polluted could be even larger than a light year, you have the possibility of time delays between what's going on in the central object and what's going on in the background. So you're not seeing a pure spectrum. You're not even seeing a pure wind spectrum. You're seeing a complex environment that's been created by this mass loss. Now, why I'm talking about this is that the other feature of massive stars is the last part of that quote. Live fast and die young, and then leave a pretty corpse. The pretty corpse is a supernova. That when these stars explode, when they undergo core collapse, because they will undergo core collapse, they're in that mass range. The the ejecta, that is the expelled envelope of the collapsar, is going to travel out through this medium. That looking at that, the central star, when it explodes, is going to have to pass its material through here. And also important, the light from the supernova is going to be seen through this medium. And one of the things we now know is that supernovae that appear to have been stripped of their hydrogen and yet are massive stars. So supernovae types 1b or 1c, or type 2s that show narrow lines, are being seen through a medium, through a circumstellar medium that preceded in its formation the supernova event. This actually changes the way we understand supernovae, because the environment is going to contain much of the material that's been stripped off the star at the time of the collapse. The winds, the winds from these stars, from the LBVs, are so intense that the composition of the surface of the star is actually going to be changed, because you're going to strip so much of the star that what you're left with in the core, when it collapses, is a fraction of the total mass of the star. In addition to which, the star, before it collapses, is going to be peculiar in its spectrum. It's going to have a strong wind, but excuse me, it's not going to be dominated by hydrogen. And in fact, it's going to look like something you may be familiar with, called a Wolf-Rayet star, that are luminous stars, extremely hot, hard radiation fields, but genuinely hot photospheres, very strong winds, and the last part of this unification paradigm from Conti is that the stars that are LBVs will become Wolf-Rayet stars that will then collapse into supernovae. So the closure here is that the role of the LBVs is that they are the precursors of the stage that sets the progenitor conditions for what will become a supernova. In principle, we should be able to see clusters of these massive stars around the sites of supernova events. In practice, we're not there yet. But studying the LBV tells us what the conditions are going to be like at the time of a supernova, because in general, you've got this problem that you discover supernovae when they've already happened, which again sounds trivial, but if the only way you understand transients is by seeing the transient and you don't have observations from before the event, you don't know where it came from. In general, this is the problem we have with certain classes of supernovae, especially the type 1As, for which we don't know the origin because we don't know what these things were before they went boom. We discover them perhaps on the rise, perhaps at peak or on the decline, but we don't discover them in quiescence and then see the event happen in front of us. The importance of the LBVs is if they really are connected with the Wolf-Rayets, then the Wolf-Rayets are, and if the Wolf-Rayets are really connected with supernovae, with type 2s, then we can piece together the evolutionary sequence. The advantage then is we can see the bright stars, the luminous stars, sometimes in the images taken of galaxies in which by chance a supernova event later occurs. The best example of this is actually a non-LBV, Sandulik minus 69202, which was the star that disappeared at the onset of the supernova 1987A event. That we know by chance that the star that exploded as 1987A was actually a B supergiant at the time, and in the range of the very low luminosity LBVs, simply because the star was bright enough and in the LMC. There are several others of the type 2s, again, because of the spectroscopy and the photometry and imaging of galaxies, just by chance, that have been caught as, as
Steve, please. It is now 22:40.
yes,
So I suggest that you mm, fi- not conclude, but finish in
you got
about 10
that.
minutes.
Francois, that's the
I
kindest
would
I've
say
ever been
from
told
10 to
by it.
15 minutes.
No, in fact, I'm going to make it even shorter. Um, this is something that I didn't get a chance to show last time, but it works perfectly well now. These are very far UV, that is Lyman. These are fuse observations, so they're in practically at the at the Lyman jump. This is 900 to 1180 angstroms. Uh, these are resonance lines in the far UV. For this line, for example, is the Lyman beta line. Um, but this is what I mean by extreme mass loss observed in stars, for which, if you look in the optical, the velocity is a factor of 3 or 4 lower. The terminal velocity seen here is like 3,000 kilometers per second, where in the optical, it's less than 1,000. So this is an example, not of an LBV, but this is what an LBV would look like if one looks in the far ultraviolet. Um, just to overwhelm you, this is an example of this, one of the prototype LMC luminous blue variables. This is just a sequence covering a period of about a decade in the optical, showing the variation in the ionization state of the envelope, that you go from having very narrow lines with this very strong central emission and just barely showing P Cygni, and at the same time, those profiles are accompanied by these extremely strong iron lines, mainly forbidden iron, where then the mass loss rate goes down and the star turns blue, and you suddenly get these very, very broad wings. Yet another one of them. Uh, I just wanted to show that you see these are low resolution spectra. They're about the same resolution as Alpi, and they're not taken with the world's largest telescopes. So this is the sort of observation that you would be able to make. Okay, it's difficult if you're in Europe to make observations of the Magellanic Clouds, except maybe in neutrinos. But uh, there are stars in the galaxy that we now know, like AG-CAR, but in the north, like P Cygni, that are certainly worth following and following in detail. Because to be blunt about it, if you've got objects that are, if you have stars that are varying on timescales like this, there isn't a chance in hell that the large observatories are going to have large extended systematic archives on these. The only way we're going to know what's going on in these various stages, and Francois's discussion of the flare in T-Corbor is a beautiful example of this. These rare, fleeting events that you would never be able to see because the major observatories would never give time for something like that. They couldn't. Those are going to be captured by your community. When I said that these stars vary on timescales of decades, that's because we're looking at them coarsely on timescales of decades. But we don't know what they're doing on short timescale. That perhaps they do go through unstable events of of high mass loss rate, and then turn off for a period, and then turn back on, and we're just catching them sort of in their median state. We can see that the variations in something like this set of profiles can be fairly fast on months time scales, but we don't know what's going on there. And because some of them are, by the standards of the 21st century, small telescope targets. That is, these are in the range of 10 to 14 magnitudes. They're worth looking at. Um, so I'll just finish with an example that parallels precisely what you saw for AG Carina. Again, this is something I showed last time. M57 is an example of an ionization bounded region seen in different wavelength regions. That if you look in the optical, the ring is dominated by this inner portion that has the high ionization, and then the outer portion shows up as you go progressively farther into the infrared. And if you go really far, like to 20 microns, you suddenly see that there's a hell of a lot of dust in the interior. And if this sounds like Eta Carina and the image I was showing you, yes, it is. So if we understand the mass loss in the LBVs, we may also transport that information to understanding mass loss under extreme conditions through the whole of stellar evolution and over a very wide range of masses. So I would urge you guys to consider that these are interesting targets, and also that when you're looking at them, the physics that you're able to understand is really quite spectacular. Um, so um, I only hope that I've not been either boring or overly technical. And for one last time, I distinctly apologize for the technical failure. I will make sure that that doesn't happen on the next time.
We are still 27.
That's
Listen to you.
astonishing.
Thus, I think that everyone is very pleased to have understand you and followed your explanations. Um,
I'm
I
astonished.
have a proposal, Steve. Could you propose a list of targets
Yes,
of interest,
yes. Well,
especially white targets? It will be easier for the community.
you see, okay, let me explain one problem. The most, the bulk of these stars are toward the inner galaxy. And unfortunately, that means that they're in the southern hemisphere. Uh, P Cygni is the one that dominates the list for the northern hemisphere,
Mhm.
and it's a bright star. So photometry uh, has been done on it over many, many years. I mean, it's a standard target for the AAVSO, but spectroscopy has not been.
Mhm.
And it's for that reason that I would I would push on that one as kind of a training ground to get a feel for the way that the profiles change as you look at different lines. It's also important that you not do just a high resolution of a narrow region of the spectrum. Uh, this is something I haven't emphasized, that the advantage with the modern instruments is that you can either tilt the bloody grating or you can use low resolution and cover a very broad range. These are stars that don't require very high resolution data, precisely because they have winds that are reaching fairly large velocities
Mhm.
of order 1,000 kilometers per second. If you have something like a resolution of a few thousand, which means LIRES um, or LISA or one of those, you would be able to do observations on, say, a single observing season with a cadence of a few days and resolve substructure in the line below the terminal velocity and actually see whether there are ejection events within the time of the mass flow. Uh, some of this has also been done for the O stars. Um, I was thinking, for example, of Paul Lucas, or who's done it um, for the Wolf Rayet, specifically for Gamma Velorum. Uh, and that's also that the Wolf Rayet stars are ideal targets, specifically the WN Wolf Rayets. Um, unfortunately, many of which are binaries, but that are that that are clearly related to the LBVs and to the massive stars in general. So I'll put together a list.
Thanks a lot.
Oh, I should add the pornography here is mentioning something about magnetic fields that we now know that O stars actually do have surface magnetism. Uh, that's very that's clear from observations over the last now 20 years, but it's becoming progressively more obvious in like the last five that we don't know the origin of the fields, but we do know that some O stars in the 10 to 20 solar mass range have fields that are thousands of times the solar field. And this changes just about everything I said, um, in that in low mass objects or in asymptotic giant branch mass loss, it's neutral or low ionization. So the winds are freer than they would be if they're ionized. And we don't know the role that magnetic fields are playing in structuring these winds. So that's yet another important point. And the third is that massive enough, and these are the stars that are going to collapse to form black holes. So they are, in fact, the precursors of gravitational wave events as well. And we know that some of the massive stars, sorry, we know that some of the LBVs are binaries, and we know that virtually all massive stars are multiple systems. So the study of these stars is, in effect, looking at what the patient looks like before it undergoes black hole formation and potentially becomes a gravitational wave source. Just as a justification for why you might explain to your nearest and dearest why you're going out in the middle of winter to observe these objects. I imagine for those of you who have uh, companions of one sort or another, you periodically have to explain your obsession to them. So you can always say, I'm going out to observe a pre-black hole, uh, or who knows if this thing's going to go through a supernova. I have to be there to watch it.
Mm. No luck that she understand.
Um, please, could you tell us where to send our spectra of P Cygni? On which
Um,
site?
for any of those, I will defer to Francois. Um, but because I think the AAVSO is trying to build an astronomical spectroscopy database analogous to the photometry, but it's still in relatively nascent stages, primitive stages, and it doesn't have the same spirit as the glory that Francois and ARAS have created. So I would urge you to collect these in the same systematic way that you have for other sources and treat these as simply the equivalent of symbiotics and put them accessible in the ARAS uh, spectroscopic database. If it's okay to say that,
Okay.
I hope.
A new garden for me. Thank you very much, Steve. Yes, uh, I think it is very interesting. And yes, clearly, I will add a subfolder in the database for LBP. Yes, no problem.
What I'd suggest is you
Our database
call them massive freeze,
peculiar
you
is
know?
that I don't want to get spectra of all stars.
No, no.
Why?
My
Because
suggest, wait,
I
hold
want
on.
to get an eye on the quality of the spectra.
Let me,
And I am not
Francois,
able, please, Steve, I am not able in my mind to check the quality of very different stars. If one send me a spectrum of a symbiotic, I can see in tenths of second, is it the good target? Is it the good resolution? Is it the good wavelength calibration? I don't need anymore. So, yes, we can add luminous blue variables to our database.
I would suggest a very limited set of additional stars, of which, because they are so easy for you to judge, I would also add the certain Wolf-Rayet stars because they are effectively the same thing as judging the quality of nova spectra. If it were anything more complicated, you notice I didn't mention things like A supergiants, where it really is much, much more complicated to understand whether somebody's reduced the data correctly or not. These these would be, if systematically cultivated, a superb and permanently valuable archive in the same way as they are for the symbiotics. So certainly not every class of star, for God's sake, that's the equivalent of a grab bag. This isn't the way to do science.
Yes.
Steve,
Yes,
I
please.
should mention that there are probably several hundred entries in the British Astronomy Association database, primarily by Juan Quarro Flo and James.
Yep.
Yes. Woody, this is not the problem.
No, I understand where you're coming
Having
from, Francois.
having a global database is not a problem. This is just an informatic issue. This is not difficult. The difficulty is to check each spectrum in order that a spectroscopical database has a fiability, I would say, over 95%. And it is easy in a photometric database to see very quickly if one result is good or no. I don't speak of the really fine value of the photometry. But it is very easy to see in, for instance, AVSO database that some values are okay and other ones are not. But for a spectrum, it is much more difficult. And what I have tried to do with our database, now more than 15 years, is to assure that the quality is good at a level of, I say, 95%. This is not a competition. Global database as BAA or AVSO, that's okay. Guys, put spectra. But from professional point of view, we have to assure the quality of the spectra. Okay, that's all for me.
Is there anything that I can add to this? Are there points that I might be able to further explain?
Francois, I agree with you 100% on your concern. And it's something a group that we have started is really focused on, both in the quality of the data, signal to noise ratio, calibration, and processing software to use.
Yes, I agree.
I should add that we're in a new age now where the scraping of data archives is going to become progressively dominant in the way that people are doing science, especially in astronomy. And many of those who are running the AI tools that are doing the scraping don't understand the physics of or the data in these archives. Many of them have never actually reduced data themselves. So they don't really, they're taking what they're getting. And consequently, because you're doing these as open contributions to a broader community, although I hate to say it this way, it's the truth that you also have to take the responsibility to ensure that that data is of uniform quality, which is just what you guys are saying. And I think that's the core, that's the core issue in the philosophy. That is the core philosophy, that it isn't just that it's trustworthy. That's irrelevant. It's that it's transparent. That somebody could go back and understand how that data was created. That's really the most important thing in setting these up. And that is, in fact, what you've all been doing. But that's, well, enough said. We can go into things like issues of calibration and data reduction procedures in a different context. But I'll add that this is especially important when you're looking at objects that vary. Now, anyone can go and take spectra serious and multiple spectra, and so they can do the quality assessment for themselves. But if you're observing an object that's continually variable, and it's a spectroscopic variable, you have only the quality of the data reduction and the systematics of the data reduction to guarantee that the data that's coming out is trustworthy, so that if you see a change, you know that it's not something that's from systematics, that it actually is something that has changed. It's especially important in the database that ARAS has set up and that Francois, you're curating.
Yes, in fact, in summary, we have the first problem, which is the identity of the star which is observed. And I have had many examples in which guys, including the best of one, sent me another star. Well, if it is a symbiotic among the 100 of symbiotics that I know, I see immediately if there is a problem. I look at each of the spectra. I'm not sure that generalist database do the same thing. I know that best database, the database for BE star, the guys and girls are doing the job. I'm sure of that. This is the first point. Second point is the wavelength calibration. Globally, it is correct. Globally, can be improved. The third point is the resolution. I get too many spectra, essentially from ALPI spectroscope, which are not at the best tuning of the resolution. Some of the ALPI spectra mimics a very good star analyzer spectrum.
Hey,
Because
Francois. On that note, what would you consider too low resolution for ALPI spectrum to submit to you? 400, 300?
I cannot exactly respond to this question because there's a problem with ISIS. ISIS gives the resolution at one point of the spectrum near H alpha line. And I think that there is really an important improvement of the resolution in ALPI spectra, looking in fact at the main line of Walco spectrum near 5,400. Yeah. This is very important. With ALPI spectra, there can be two things, in fact, two problems. The first one is the tuning, in fact, of the focuser, the internal, the collimator first. The second one may be a defect in the device in itself. So one thing I can produce to you for LP observers is a very good Welco spectrum, both in 2D and 1D spectra, in order that you check on the table what is the resolution of your spectroscope. Second thing, very important for LP, LISA, and so on, is to check at the beginning of an observing sequence the quality of your collimation. The first thing is you have the telescope pointing to the target. First, you get a spectrum of the Welco. And with this tool, you compute the FWHM of the line at 5,040 angstroms. And you check if your collimation is okay and you tune it. This is really very, very important. Last but not least, the quality of the instrumental and atmospheric response. This is really a great issue. Well, the history of spectroscopy, I would say 15 years ago, was likewise 3, high resolution, 15,000 to observe H alpha line in B stars. This is the real history of spectroscopy. Some guys, especially observed, no, this is essentially the history. Now, this is another field with especially we have many low resolution spectra. Frankly, to be honest, I prefer LISA to LP. One could think that 400 resolution and 1000 resolution is about the same at 30%. Really, for the stars object that we observe, it is a significant difference. Well, LP is very interesting for white lines and very interesting if you have also for variable stars the magnitude in V-band in order to calibrate the spectrum inputs. But getting a good photometry in V-band is not sufficient. The main issue is really the SED, the spectral energy distribution, along all the observed wavelengths in visible. And sure, we have really very important improvements to do in the next years. I don't know if it is possible, clearly. I have all the series now of TCRB. We have 1,050 spectra, and I can say that it is very difficult to calibrate in flux this spectra
Well,
because the SED, the atmospheric correction, is not very good for most of us. And I say most of us, and of course, I include me in us.
to come back to this same point, the way that the way calibration should be done for objects for which the spectral energy distribution can change with time or that are sufficiently complex, either like novae or Fouriers or whatever, is by using standard stars that are observed at the same time and not using photometry. That that guarantees that you get from the instrument a completely self-consistent determination. So I realize that this can be very difficult, but it doesn't have to be at precisely the same air mass. It simply has to be observed under the same conditions. And it means that you're going to be observing targets that aren't the target of interest. But by doing that and by doing standards, you get a completely self-consistent calibration where when you do photometry, you're at the mercy of all of the uncertainties in the way that you've reduced the spectrum to get the band in which you're going to do the comparison with the photometry that's been published. So if you use, say, AAVSO and you have two or three or even one photometric filter, it isn't just that your uncertainty comes from the uncertainty in the photometry. It also comes from the comparison between the filter that was used to produce that photometry and the one that's going to be synthesizing your spectrum magnitude, because you have to fold this through a filter profile, and you don't have that information. You're
Steve,
going to
Steve, will helping transform our photometric data make that a little more accurate in
a
terms
little bit
of
more accurate,
photometry?
yes, but ultimately there's only one way to calibrate a spectrum, and that's with a spectrum. It's that simple, that if you've taken the spectrum of a standard star, in other words, one for which there's already an archival determination of an absolute flux, then it's trivial because there's nothing synthesized in that. You
Well,
don't have
I
yeah.
think a lot of us do that, especially for TCRB. I take a spectrum of alphaca every other night, or with
Oh,
the
it's got to be
spectrum.
at this is the key point. It's got to be at the same time.
They're only about a degree apart. So I
When
think
I say
the
at the same
condition,
time, I mean under identical conditions.
right?
When observing novae, for example, one of the things I do with my colleagues is to observe the standard or a standard, the nova, and then the standard that will be at the same air mass as the nova was at that time, and then do the extrapolation between. That's extreme. You don't need to do that kind of crap, but it does have to be under the same conditions. Otherwise, you can't be sure of the systematics because the atmosphere changes its transparency characteristics. Um, there's an exercise I gave my students that you might find really enjoyable, especially now, because you've got Sirius. I gave them the exercise of watching Sirius as it's set, taking spectra every couple of hours, and from that, determine what the absolute calibration of Sirius was without using any other standard. Because you can get the atmospheric transmission by using the change in the spectrum as a function of wavelength, and then extrapolate that to zero, as in extrapolate to the top of atmosphere. You can do that with like 3 spectra, and it actually works. But once you've got that, I think it gives you a good feel for what the different contributions are and why you really do need to observe at the same time. But having the spectra, even if they're on different nights, if your site is sufficiently stable, that's certainly better than just doing the photometry. Now, ASO has an interesting way of doing this, but they're at Paranal, and Paranal is like 1 step below Paradise, so it really doesn't matter which direction you're looking in. You know, the sky is already perfect, so you can't get more than perfect. Um, they don't necessarily take it even in the same direction. They just try to get sort of the same air mass, but it's anywhere in a circle above the horizon. You can get away with that if you're at 5,000 meters and in the middle of the Atacama. But if you're sitting in, say, the Normandy coast, and you're under an atmosphere that's being fed by the English Channel, you don't really want to do that.
I agree. Well, an excellent subject. I will send you by tomorrow the quality of TCRB spectra. There are good one, perhaps 10%. I speak about the instrumental and atmospheric response, of course. All are good, no problem. But about the quality of the spectral energy distribution, I think that we have about 10% of them which are good. The problem is which one are good. And clearly, at the date, I don't know. I'm working on the subject.
Yeah, Francois, you probably have to compare 5 of them taking at the same time, and if 3 or 4 agree, you throw the one that doesn't agree or 2 doesn't agree out, I guess. Very laborious.
Yes, this is a really difficult problem. Clearly, even professional teams are still working on the subject. And about, say, correction of the spectrum with spectroscopic standards, I think that you can check what is the study which is done for each great observatory. There are teams with several astronomers taking, I would say, Steve, correct me, hundreds of spectra over a large number of lines, several lines, in order to qualify their sky.
It's actually much more than that. Um, you can use actually as the extreme example, JWST or HST, where just monitoring the instruments by observing standard stars in an environment that has no weather is the same thing. You're looking at the systematics. So you pick cosmic sources that you systematically observe, and you use that to set the calibration as a function of time for the sensitivity of your instruments. Uh, yes, this first in the quality of the site, but then in being sure that in the databases that are in the archives, that the high-level science products, that is those that are wavelength and flux calibrated, are calibrated with standards that themselves are systematically checked against each other. Now, the single hardest part of astronomical observations is absolute calibration. Wavelength calibration is actually extremely easy because astronomical spectra are photons and the instrument is measuring photons. And so if you have a lamp, it's the same as observing a star. Since you know from the laboratory what the wavelengths are, the calibration of which is in effect a geometric correction of the spectral image, is quite straightforward. It's knowing what the sensitivity variation is that's a completely different issue. And also, I should add that you saw how complex these spectra are, comparable in complexity to what you have in symbiotic systems where you have a red giant. You have to realize that you can't normalize these spectra. People do all the time. In fact, the spectra I was showing you were from an atlas by Walborn from only about a few years ago. And all of those are normalized, but they weren't being used for the purposes of quantitative analysis. They were being used for qualitative spectral display. Uh, that's the reason why the calibrations are so important, and also why every calibration introduces a different class of error. It's not random, it's systematic. The uncertainty in the calibration propagates in the error budget, even if it were a perfect spectrum. I mean, you could have a signal to noise of hundreds in a calibration spectrum, but if the 0 point is wrong or the slope is wrong by some factor, that's going to show up as an uncertainty systematically in the spectrum to which that standard has been applied. It's not to be discouraging, it's just the opposite.
Yeah.
Once you get
So,
into the habit, it's no different than observing the same star twice.
so Steve and Francois, in a perfect world, when we take spectra, we would take a star at the same time, that has a calibrate, flux that's already been flux calibrated, in the CalPERS catalog or any other,
Mhm.
and provide Francois our resolution with our calibration lines or Relco lines. A true resolution, not the ISIS resolution.
Mhm.
Well, also the resolution is really just a phrase. Once you've got the spectrum, you can determine the resolution for yourself. So it's just a number that you use conveniently for the database. Uh, If you have in a shell spectrum, the resolution is definitely variable from one order to another. And even uh, if you have an absolutely perfect grading with no curvature effects, then even there, the resolution is true only in a narrow wavelength region. Because if you're using, say, the Alpi, it's a grism. So it's not a diffraction grating. It has prismatic dispersion. And the atmosphere is also going to screw it up because that also introduces prismatic dispersion. Even in a perfect world, it's just a question of being careful, and you all understand that. Otherwise, you wouldn't be sitting through these discussions.
Steve, this is Wayne Green talking. We ran into some issues with some of the spectroscopy several years ago. COVID came along and did us the favor of letting us sit still for 3 years and build a spectrograph. We've been using that spectrograph in Chile now for the last 2 sessions of 10 days each. For spectral calibration, we're simply using A05 stars because there's no known calibrator that's decent enough for us to use that is of a magnitude high enough to get a sufficient signal to noise ratio to apply to that.
Well, let me
During
ask.
the evening, we've noticed one thing quickly. During the evening, we have noticed that our spectrograph will shift its focus, and we have built into something a little motorized focuser. And it's often the case that we'll have to stop, spend about 20 or 30 minutes, and refocus the calibrator. Seldom does the camera lens need to be refocused. Matter of fact, we state, "Thou shalt not focus the camera lens." And to that degree, we've noticed a little bit of sky variation and so forth, even though we're at 5,000 feet. It's just something that comes with the game. And so you're right about your error budget. I always say ignore the signal and pay attention to your error budget, because your error budget can really defeat you if you're not careful. So those are just some of the things that I wanted to kind of throw out there for discussion here.
So you're using Southern Hemisphere. Have you looked at some of the brighter stars among the ESO standards? Because there are A and B stars in that are in the like 6 to 10 magnitude range.
Handfuls of them, yes, but they're all over this. They're seldom anywhere on the sky. So we were able to come up with a catalog of quite a few A05 stars. And the reasoning being is that we're seldom more than a few degrees away from one of them. So we can slew over.
Yeah.
Our observing regime is we take a spectrum and 3 spectra followed by 3 calibrations just to take care of any cosmic rays we may see. Then we slew over to a reference star and we do 3 exposures and 3 calibrations.
Okay.
And occasionally throw in a flat.
What wavelength interval are you working in?
Roughly 3,400 up to that atmospheric blip at around 76 to 78.
So these are
angstroms.
What resolution? I mean,
we'll talk about that.
Or no, or again, order
no,
of
but I mean,
magnitude.
technically our instrument is good for 2,500, but we're seeing it a little bit blurry right now.
Okay, so in other words, you're working somewhere between 1,000 and 2,000.
Correct. One of the other issues that we have is we have a 1 arc second slit. And even though we achieve 1 arc second of seeing from time to time, we are cheating the aperture occasionally when the seeing goes sad. And the 1 arc second slit is dictated by the ratio of the calibrator to the camera lens. We need to build a bigger spectrograph to get a wider slit to keep resolutions high.
Well, actually, you really need to worry about something slightly different, which is the slit loss. How do you judge that?
Finger in the wind.
That's a problem.
That's a problem.
Because that's going to be different between your standard and the star.
Well, being paranoid about the slit width, we also work the meridian primarily.
No,
So,
I mean I didn't mean the width. I meant the length.
oh, the
How
length of the
how
slit
do you
is
judge
huge.
your slit loss? Because 1 arc second is a fairly narrow slit,
Yes,
even for a good site in Chile.
correct.
So I would expect your seeing is somewhere between 1 and 2 at best, which means you're probably
Sub
going,
1 to 1.5.
okay,
And
fine. That
beyond that,
means,
the wind's too frisky. So,
okay, so that's giving you maybe 10 to 20% slit loss.
okay. Yeah.
Um, okay, but you can get that information by doing a measure of the point spread function off your spectrum.
Yes.
Okay, so I would suggest if you haven't already done it, add that to your procedure.
It's something that's on the list. So there we go. But the real problem that we seem to be having is getting the okay. So what we've noticed is if we slew from one part of the sky to another in say declination,
Yep.
um, then what will happen is our slit will shift on our guider by a small amount.
Yeah.
And the reason for that is a construction error that we made in the guide camera mechanism. But outside of that, the instrument seems to be holding up well and performing well. The
Hmm.
problems that we face are the grading curve, which is, Thor Labs grading has a fairly strong curve to it, and the fact that we're using a CMOS camera that is a little deficient in the blue and in the red. So correcting for that is going to get us. To compensate for that, we expose deeply. So I'm looking at around summed for the entire height of the dispersion axis, something on the order of about 25,000 ADU at the 3400 and about the 7800 part of the spectrum. And that boosts our signal up. We have a noisy camera. We found that the voltages on that camera have been low. We're sending a power supply down here in the next few weeks to compensate for that. So I'll tell you, you say, when you observe, pay attention to your instrument. We built this thing and had high expectations of it, and now we're beginning to see where the shoe really pinches the foot.
Hmm.
So, here we go again on another design, but we want to take data and do what we do. I won't go into the subject of what targets that we're going with right now. We'll be publishing those this fall or this spring, I should say,
Well,
summer.
what are you going after?
I'll talk to you about that in private.
Okay.
I've had just too many people walk all over my data before. I'm not want to get exposed in that. But they're interesting stars. Let's put it that way. We have the southern hemisphere to play with, and that's another thing too. Is like we're like little kids in a candy store because we have all these new targets we can look at.
I'll tell you a little story. Actually connected with the LBVs. The first time I actually observed them directly was when I had an observing run at Tololo that was for something else. And I the weather was so good that I was able to finish all of that work in instead of 2 weeks, like 10 days. And I spent 4 nights doing what I referred to as, at the time, as paddling around the LMC, kind of looking at spectra of everything that I had always wanted to see a spectrum of. Um, the greatest single advantage you've got is that the Southern Hemisphere has not only the galactic center and the inner galaxy, but um, with the exception of Andromeda, it's got the brightest members of the visually brightest members of the local group. So you can with your system, you should easily be able to get the brightest stars in the LMC.
We're finding difficulties around magnitude 11.
That's just about the where these are going to be, or even
Yep.
some of them brighter.
Yep.
Okay, but what's the aperture that you're working with?
Uh, 0.6 meter, 24 inch.
You should be able to get these within an hour at reasonable signal to noise.
We are doing pretty good for we're limiting ourselves to about 11th magnitude for the campaign stars, and there are plenty of them above that, so we're target rich in that area. And there we're spending 600-second exposures times 3, and getting good results, good SNR results.
Sure.
So we're happy. I'll tell you what you just said though about we were finishing up last night and too close to the end of, or beginning of twilight. Plus, we were doing bright time observations, and we thought, "What the heck?" And we went after a CV. So I'll send you some of the results on that.
Okay.
Just a random one we found near the field, and we said, "Oh boy, let's go look at that." And then we were just astounded by what we saw. So it was a very interesting experiment. And I've always heard, my mentor taught me, said, take part of your night and just take a picture of a target, just learn something, just explore.
Mm-hmm.
That's where HH212 came from, is because somebody lost control of their observing list and turned the camera over to one of their friends for 45 minutes. So those are things that, I'd like to point out just for the general community, is to pay attention to focus of the collimator. It shifts pretty badly with temperature, and it's very difficult to adjust on some instruments, and it's just it'll bite you every time. So thanks, folks.
Hey,
Okay.
Steve,
Yeah.
Thank you very much, Guy.
one little thing, Steve. Here's what I got for my E-shell on the resolution, the differences between 29th order and about 59th order. It varied between, I think, 12,500 and just above 10,000.
Yes.
Yeah, so you're right about that. And of course, the worst one is kind of in the middle for some reason.
Yeah. The other aspect of Murphy's Law,
Mhm.
wherever you really need to observe, that's going to be the worst spot.
Yep.
No, just a point.
Very good.
The resolution in HL is computed for each order.
Yeah.
Thus, I propose that for this order, you check the list of your calibration lines. Perhaps there is only one bad calibration line, which provokes a bad calibration in this order and produce a bad value for the resolution. You have to compute them line by line.
Mhm.
Right.
Okay, we are far from
Yes.
luminous blue variables, but it has been very interesting. I have a problem with Steve. Just one, that most of us have not spectroscopic, photometric sky.
Yes.
Yes.
Right. Like
We are
none of us.
at a low altitude, okay?
Francois,
4,000
I'm in Pisa,
meters or more. We have humidity in the sky because most of the cities are built near rivers,
Mhm.
and the sky is not photometric, of course. In time and also in sorry, direction. And this is really difficult to produce calibration according the highest level, which is using spectrophotometric standards. Are you there, Steve?
I'm deeply sympathetic. I'm in Pisa. Yeah,
Hmm.
so yes, but there's an unfortunately military phrase: the difficult we do immediately, the impossible takes a little longer. Uh, it is difficult, and it doesn't have to be done for everything. But when it's worth doing correctly. And it sounds difficult, but it really isn't. That's all I want to emphasize. It does not always have to be done, but when it does need to be done, it should be done correctly.
Mhm.
And it's clear that that's understood.
Okay.
Just let me just remind you that virtually all of the work that I was talking about, for these stars, involves long archives. Again, I said decades. One is looking at data that was taken with photographic plates in the period before 1990. So you've got to keep in mind that a hell of a lot of this data actually was never calibrated. And one of the difficulties as a legacy from that era is that many of the people who are still in the business, some of whom have produced students as well, have retained this attitude that what you do is normalize the data and you do the comparisons of the line profiles based on that. You do things like drawing the continuum. You use equivalent widths, and these introduce systematics that really have to be understood, but are largely unnecessary because you have instruments that can do what 30 years ago could not be done. I need to emphasize that. CMOS or CCDs are remarkable instruments in that they are digital. And consequently, you can do, even if you do it systematically at a relatively low level, so photometrically or spectrophotometrically, you're still producing data that will have archival value in a way that even the photographic data can't possibly, because it was mere morphology of the spectrum instead of something as quantitative as energetics. That's the great advance of the century.
Thank you very much, Steve. I think that we can conclude
Yeah,
on this
thank
subject.
you to everyone.
En français,
Good
je
stuff.
dirais, nous avons encore du pain sur la planche. In English, I look at the translation. We have our work cut out for us. Is it correct?
Yes.
Yeah. This is a really pleasant subject for the years and years.
And so good night to all. And again, for the very best wishes for whatever this new year will bring, and may it be better than anything you hope for.
Thank you very much, Steve,
We'll
again.
see each other in a month, right?
And next month, supernovae.
Okay.
Take
Good.
care.
See you.
Thank you,
Thank you
Steve.
very much again.
Good night.
Thank you, Steve.